Let's talk about thin film interference in this segment. The basic principle that we need for thin film interference is the relationship between path difference and phase difference. If you look at a portion of the wave from 0 to 2 pi, it's clear that a phase difference of 2 pi corresponds to a path difference of lambda. Similarly, a phase difference of pi corresponds to a path difference of lambda by 2. In general, the relationship is as follows. The phase difference is equal to 2 pi by lambda times the path difference. So you can substitute the path difference equals lambda, you get the phase difference 2 pi. The path difference is lambda by 2, you get the phase difference equal to pi. And for any other path difference that's not one of these, you'll get some intermediate value of the phase difference. That's a very basic principle that we need for studying thin film interference. Here's a picture of the schematic. You have a thin film, which is basically a layer of oil or even a coating of some kind on a substrate. The substrate is given the refractive index N3. It could be a soap film hovering around in air, in which case N1 and N3 will still be air, and N2 will be the refractive index of water, which is about the same as soap film. So the thickness T of this film is supposed to be either known or determined, and we have to find out a condition that light incident from medium N1 or medium N3 will be reflected off either constructively or destructively. So one way to study that is to find out what happens to a light ray that enters this system. So let's say the light ray enters from here. Now by Snell's law, it's going to be refracted. Let's assume that the medium N2 is bigger than N1 in refractive index, so it'll be bent toward the normal. And then let's assume that the medium N3 is less than N2 for the sake of drawing something, and so it'll come out like that. That's one possibility. The other thing that also happens with the laws of optics is you don't just get refraction, you also get reflection. All three things happen simultaneously. There's reflection, refraction, and transmission. This is called transmission. So here you're going to have another reflection. This is sometimes called a secondary reflection, and that's the primary reflection. And then you'll have a further transmission. Now these two rays that come out can be observed by the observer. So I'll draw that like a cartoon sketch of the eye. The observer can observe it. If these two waves are in phase and they don't have any phase difference, then it'll appear to be constructive or bright. Or if they have a phase difference of 2 pi or multiples of 2 pi. Or said in terms of path difference, if the path difference is either nothing or multiples of lambda, then you're going to have a bright reflection. So this would be a case where you want good reflection. Sunglasses are an example. If you want to hide from somebody, then you wear sunglasses, and one of the properties of a sunglass is it hides your eyes because the reflection is so good. So if you don't want to hide your eyes, then you want to have a coating whose thickness is such that the kind of interference you get here is destructive. So you can have both types. And then lastly, this ray is going to have a tertiary reflection, which is going to be here, and then it'll anti-Snell like that, and then an observer over here can now observe these two pairs of rays. Whether they constructively or destructively interfere is another story. So these are all the things we have to explore. Now there is a little fact I need to tell you, and that is if light goes from a medium that is of low optical density to a medium of high optical density, it is like reflecting a rope off a heavy wall. So the optical density can be thought of as the sluggishness of the medium. So this medium is very sluggish, being a heavy wall, and you tie a clothesline to it and you start moving the clothesline up and down. What happens is that the wave, when it reaches the wall, it just rebounds. And when it rebounds like that, because of conservation of momentum, it rebounds, you have a phase change of pi, because it inverts itself. So one of the ways to remember this is when you go from a low medium to a high medium, you get a phase change of pi. So it says, it's remembered like this: low to high, phase change pi. What about high to low? Suppose you have something wiggling around in jello and then it comes out suddenly into the air. There'll be no phase change because air will not oppose the motion of the wiggle. So it will not have any phase change at all. So that's the other principle. High to low, phase change of 0 or O. So low to high, phase change pi; high to low, phase change 0, O. So that's our principle here. Now let's, for the sake of analyzing this, we have to put some kind of conditions on N1, N2, and N3. Let's just take the following example. The other possibilities are explored in the notes. So let's take N1 is less than N2, the way I've drawn it, and that they're at anti-Snell's. So N2 is bigger than N3. Let's take that possibility. Now let's look at each of these rays and study its phase change. I'll indicate phase change in a certain manner. If you go from it's going from low to high, that's low and that's high. So this is going to have a phase change of pi upon reflection. So I'll put pi here and put a mark like that. Now what about this ray? It's going from this one, the one that's transmitting through, it's not reflecting, so transmission rays have no phase change. It just goes right through. And then from here there's a boundary, and this boundary, what happens is there is a it's going from high to low because N2 is bigger than N3. High to low, phase change O. So this has no phase change. Now what about this one? Here it's going to reflect. The transmission ray has no phase change anyway, and then it's going to reflect here because it's high to low, phase change O. So we'll put that there. And then here it goes transmit through. If it transmits through, it's got no phase change, so it's 0. Then it reflects again, but it's reflecting from low, from high. This N2 is higher than N1. So this high, so it's going to be low to high. Wait a sec. This is N2 is bigger than N1, so it's going to be high to low, phase change O. So this again has 0 phase change upon reflection. And then when it comes out, it again has 0 phase change because transmitted rays don't have any phase change. Maybe I should put that as an additional condition. Transmission, no phase change. So these are all the different phase changes. So once again, let's run through this because it's pretty important. Here it's a phase change of pi because it's going from high, from low to high, because N1 is less than N2. So N1 is low and N2 is high. So the phase change is pi. And then here at this reflection, it's going from high to low because that's high and that's low. So phase change of O. And then the third reflection is again high to low because this is high and that's low. So phase change of O. And then the transmitted rays don't have any phase change. Now the phase difference between two rays is what determines whether you have constructive or destructive interference. Let's label this ray 1, let's label this 2, let's label this 3, and let's label this 4. So the phase change between 1 and 2 is equal to pi. Well, that corresponds to a path difference of lambda by 2 because pi corresponds to lambda by 2. And then you don't have any phase change between 3 and 4 because that's pi minus 0, that's 0 minus 0, so that's 0, and that corresponds to a path difference of 0. So that's the results of all these analyses. Now lastly, there's one more concept, and that's called optical path length. The concept of optical path length is as follows. if light goes through a medium, it actually appears to be going for a longer time because it's going at a slower speed. So if it's going through a medium that's got a high refractive index, it's slowing down, which means that its equivalent path length in vacuum is going to be bigger. So the optical path length is defined as the refractive index of the medium times the actual thickness of the medium. So now let's try to find out the true path difference between rays 1 and 2. What is this going to be? It's going to be compounded of two effects. One is the phase change, which we've already calculated, and the other one is going to be the fact that ray 2 has got this additional path inside the medium. In fact, if the incidence angle is very small, that additional path is just 2 times t times the refractive index n2. So the true path difference between rays 1 and 2, so it's going to be 2 times t n2 plus or minus, because I don't care to which one I'm going to add pi by 2, plus or minus lambda by 2. Lambda by 2, not pi by 2. And that's the true path difference. This I'll call capital delta. Now, if capital delta between the rays 1 and 2, so I'll call that delta 1, 2, that's the true path difference between rays 1 and 2. If that is equal to a even multiple of lambda, so lambda by 2, so it's 2m times lambda by 2, which means it's m lambda, then you get constructive interference. If it's an odd multiple of lambda, which means odd multiples are like 2m plus 1 of lambda by 2, which is m plus a half lambda, then you get destructive interference. Let's try to find the thinnest coating I can put on a glass like this so that it reflects. In other words, the interference is constructive. So I want to hide my eyes behind sunglasses because I've done something shady. Okay, so I want the reflection to happen. Now, the way that's arranged is to write 2t times n2. That's the path difference in the medium, plus or minus lambda by 2 will be equal to, if we want constructive interference, so I'll write it as m lambda. So now the thinnest can be solved for, so I'll write this thickness as 2t n2 equals m lambda minus or plus lambda by 2 so m equals 0. Let's choose m equals 0 and the plus sign, so I'll get 2t n2 equals lambda by 2, which tells me that the thickness t equals lambda by 4 n2. This sort of result is very important. This is called a quarter wave plate in optics because of the lambda by 4, that's where the quarter comes from. And a wave plate refers to the smallest thickness of something that will cause reflection. Lambda by n2 has got a special name that's called lambda medium. So what you do is you take the wavelength of the light that's coming in, which is lambda in n1, and divide it by the refractive index of n2 to get lambda medium. So if you want, you can say the quarter wave plate thickness is simply lambda medium divided by 4. So that's the smallest thickness I should coat my optics with to provide reflection. And this is used in binocular theory and telescopes and other places. Now notice that this is not the only thickness. For different other values of m, you can get bigger thickness. Now if you want a good pair of sunglasses, they'll have this coating that's somewhat thick. You can't have it too thick though, because if you have it too thick, then it will not be too sensitive to what lambdas get filtered out. So you've got to play it just right. It needs to be a thin enough coating, but of very high quality.